right, can you guys at home hear me? And see me? And see the screen?
Yes.
Good. Anybody else? Okay, thanks, Taylor. Okay, so then I must have done something right. Now let's just hope I'm recording it correctly. It does better when I record on Zoom. I'm hoping I'm doing that. It says stop video, so I guess it's going okay. All right, so my plan today, make sure everybody knows that we've got a test scheduled 1 week from today, Wednesday the 21st of October. We're right on track. Today I'd like to go back over a few more examples in section 7.7, and then start and possibly finish section 8.1, and I'm going to review on Blackboard. You feel like you're ready? Can you integrate just about anything I throw up at you? Okay, okay. Do you have any questions on anything that's going on in homework or what we've covered that you want me to go over? Any questions from my home group? Let's try to pay attention to the old chat thing. All right, we're good. We're all good. Okay. We were talking about improper integrals, and we had two types of improper integrals. Those that have integrands, which become infinite, and those that have limits, which become infinite. And so we have ways of computing these improper integrals by using limits. We had to review some of our limit skills from Calculus 1, I suppose. We also have to have some idea of what our asymptotic behavior of some of our functions are. So we need to know kind of what the graphs look like of e to the x and e to the negative x and inverse tangent, a logarithm. Those are all kinds of things that show up in our integrals, and we have to make sure that we know what happens when x approaches a particular value or if x goes to infinity. And that will be reiterated when we get to chapter 8 as well. We're going to do lots and lots of limits. So my first example is the integral from 0 to 1 of 1 over the square root of 1 minus x. Looks like a very harmless integral, but I say it's an improper integral, and you need to tell me why. That's right. When x is 1, my denominator is 0. So that's an example of an improper integral. That was the one we call type 1. The integrand becomes infinite. And that's what makes it improper. Now, in order for me to work this out, I'm going to need a little bit more room. So let me grab a blank sheet of paper, and we'll work it out on it. So it's x is 1. That's the problem spot. So we take the 1 away, and we make it a letter. So we rearrange the integral so that it looks, say, from 0 to b of 1 over the square root of 1 minus x dx. And then when we calculate that integral, we'll get the antiderivative, and then we'll let b approach 1. I'm coming into 1 from the 0 side. So really that's the limit as I go into 1 from the left. Quit doing that wiggle stuff. Then to do this integral, we just take u to be 1 minus x. Du then is negative dx. So I'll put the minus sign with the du. And we're going to integrate minus the integral of, let's write it as u to the negative 1/2 du. And then when we're done, we'll put that limit back in here. I didn't need to leave any room for it. Just power rule integral, add 1 to the negative 1/2, and we get a positive 1/2. And then when we divide by that 1/2, we get a 2 in front. So we get 2 times u to the 1/2 with the minus sign. But u was 1 minus x. We'll go ahead and write that as a square root instead of a half power. And so we're going to come in from 0 to b. The b will go in first. When I subtract, I get a plus sign here and a square root of 1 there. Can you do that limit? As b goes to 1, 1 minus b goes to 0. Square root of 0 is 0. So this becomes 0 right there. And so we get 2 times the square root of 1, which is just 2. So the integral converges to 2. Questions? Anyone? Okay, my next example has an infinite limit. A bound up there on top. And so that's what makes it improper. I also have a denominator and a logarithm, so I have to make sure that those are both defined in that part of the number line from 2 to infinity. So I've left out the 0, right? X is 0 would give me 0 in the denominator. The natural log of what number is 0? Natural log of 1 is 0, and I left out the 1 as well. So it's strictly a type 2 improper integral. The upper limit is infinite. It's defined everywhere else. Let me pull this up. That might be better. I can see better. Okay, so again, I'm going to do that on the next page. We're going to compute that integral. I'm going to put a different letter up here where the infinity symbol is so that I can do the calculus part. Let's get out. We're going to do the integral from 2 to infinity. So I'm going to put, I usually use a capital N or a capital M for the big numbers and an A and a B for the little numbers. Okay, out of pencil lead, that's the end of class. So I set it up like that. Who's going to tell me how to do this integral? It's strictly u to u. What do you want to use as u? That's right. Take u to be the natural log of x. And then the du will give us the 1 over x dx. I forgot my dx. There it is. So here's the 1 over x dx that is the du. That leaves me a u squared on the bottom. We can put that on top and write that as a u to the negative 2. Again, it's a power rule. Add 1 to the power, divide by the new power. So I get u to the negative 1 divided by negative 1. But I'm going to write that as a negative 1 over u. Where u was the natural log of x. And we're going from 2 to n. So I'm going to write that as the limit as n goes to infinity, negative 1 over 2, oops, not a 2, natural log of n, minus a minus gives me a plus, 1 over the natural log of 2. So what do you know about the natural log of n as n goes to infinity? Natural log, just the natural log by itself, as n goes to infinity. What does the graph look like of the logarithm? It also approaches, it's a growing function, but it's slow growing. So this leaves me a negative 1 over infinity, which is going to go to 0. So this term here is going to 0, this whole term. And that leaves me a 1 over the natural log of 2, not one of your favorite numbers, but it is a real number. And that means our integral converges. And it converges to the 1 over the natural log of 2. Okay, so I've got a third example here, and I think I might even have a fourth. My third example back here on the handout sheet was that we're looking to find this limit from minus infinity to 0 of x times e to the x. Both x and e to the x are continuous for all values of x. So my integrand is well defined there. I do need a dx. It's this infinite limit here that makes it improper. So we're going to put a letter there and run a limit through that. Grab another piece of paper. one out. Proud of me? Okay, so we're going back here. Did you get that written down yet? Did I take this one away? So here's our next task. To integrate from minus infinity to 0 of x e to the x dx. I've got to make it a proper integral. Then take the limit as n goes to minus infinity of x e to the x dx. Now we can integrate, or can we? Integration by parts. It's no longer a u du integral because the x in the exponent on the e is the same power as the x out front. But we're 1 degree higher, then we can do substitution. So we're going to integrate by parts. U is always the polynomial term unless we've got a logarithm. dv then is going to be the e to the x. du is dx, and v is e to the x. And so our integration by parts will be uv minus the integral of v du. And so we're going to have x e to the x. Now that's going to have to go from minus infinity to 0, minus the integral of v du. du is dx. So before I put the limits on the integral sign and the limit of the n, I'll just compute the integral first. And the integral of e to the x is e to the x. So our antiderivative looks like this. And I think I'm going to factor out the e to the x. Now I'm going to evaluate that from n to 0. And then I'm going to take the limit as n goes to minus infinity. So we put the 0 in first. We get e to the 0, 0 minus 1, minus e to the n, n minus 1. And then we're taking the limit of that as n goes to minus infinity. E to the 0 is 1, so that first number is just a negative 1. Let me put the limit here so you can look at it. What do you think of that second limit? I'll have an e to the minus infinity times minus infinity minus 1. So essentially it's e to the minus infinity times something that's also minus infinity. What happens to e? What's Timmy, describe for me what this means? That's right. So that's going to go to 0, right? So this term goes to 0, this goes to infinity. If you remember anything from your calculus 1, that's an indeterminate form. 0 times infinity. We had two other indeterminate forms. We had 0 over 0 and infinity over infinity. Those last two indeterminate forms allow us to use L'Hopital's rule. But 0 times infinity tell us to do some algebra to put it in one of those two L'Hopital rules forms. So how can I make this look like 0 over 0 or infinity over infinity? been a while since you've done those kind of limits, huh? Usually we take one of the factors and we put its reciprocal in the denominator, right? If you divide by the reciprocal of something, that's the same as multiplying by the flipped version of it. So I'm going to put the 1 over e to the n in the denominator. Leave the n minus 1 in the numerator, and I'll have a 1 over e to the n here. But maybe it's easier to think of it as, it's just this part. N minus 1 over e to the minus n. Now the numerator becomes infinite when n gets large. Minus n, as n goes to minus infinity, goes to infinity. So this behaves like infinity over infinity. And now we can use L'Hopital's rule, which says, who remembers what L'Hopital's rule says? What's the big deal about getting it to infinity over infinity or 0 or 0? That's right. If we take the derivative of the top, divide by the derivative of the bottom, and get a limit, then that's the limit of this function. So I'll get the derivative of the top to be a 1. The derivative of e to the minus n is itself times the derivative of the exponent. So I get a minus e to the minus n on the bottom. N is going to minus infinity. This minus sign makes it go to plus infinity. E to the infinity is infinity. So this behaves like 1 over infinity. This limit is going to be 0. So if that's the star there, I've got the value of my integral then is equal to -1 minus 0 or -1, so the integral converges. Okay? So I've got an integration by parts on your web work. I've got maybe some version of this problem on your web work. Well, we've seen 3 that have converged. Let me see if I can think of one that is not going to converge. Maybe one of each type, one with an infinite integrand and one with an infinite limit. So how about we take a break here and look at, make sure you get that all written down. Good. It's different than just writing on the board, because when I write on the board, I can just walk away from it and write somewhere else. Now I gotta make sure you've all written it all down. Otherwise, I'm gonna cover it. So you're gonna speak up if I ever do that to you. One thing I've noticed in this semester, my students wearing masks, nobody speaks up. Usually my honors calculus classes are very conversational. You know, whatever. Okay, how about we do this one? Let me see. How about I look one up before I booger it up real good? Okay, let me try this one. Oh, a second ago. Where'd it go? Can't see it at all, can you? That makes it hard to do. Okay, how about the integral from 0 to 1, x over 1 minus x squared dx? I think this is going to be an improper integral that diverges. Where is this thing improper? What makes it improper? X is equal to 1 gives me 0 in the denominator. So it's improper because of the 1 down there. So we're going to take that 1 out of there and put a letter. And do that. How do you do that integral? It's another UDU. I've got a second degree power on the bottom, first degree on the top. So that should work as a UDU integral. Take u to be 1 minus x squared. Then du is a minus 2x dx. I've got the x dx, so if I take a negative 1/2 times du, then I can substitute out the x dx. So I'll put the negative 1/2 in front of the integral sign. Then I'll have a 1 over u du. Integral of 1 over u is the natural log of u. Got to put it in absolute value bars because I have 1 minus x squared playing the role of the u. Now I've got to evaluate this from 0 to b. And then I got to take the limit as b goes to 1. And again, I'm coming in from the 0 side, so technically I should do a one-sided limit here. b goes to 1 from the left. And so the expression that I have when I substitute those numbers in is a negative 1/2 natural log of 1 minus b squared. Minus a minus gives me plus 1/2 natural log of 1. The natural log of 1 is 0. So that whole second term is 0. b is going to 1 from the left, so b squared is going to be 1. Then I'm taking the natural log of 0. The natural log is 0. Well, the natural log of 1 is 0. Here's the natural log graph. The natural log of 1 is 0, and then it increases here. So as x goes to 0, or x goes to 0 from the left, the natural log of x goes to minus infinity. So that's what's happening here. This is approaching 0 from the left. The natural log of 0 goes to minus infinity. Actually, it's multiplied by a negative 1/2. So it's going to become infinite. And this integral diverges. So what if we did that same integral? Save us a few steps. What if we did the integral, say, from 2 to infinity of x over 1 minus x squared, since we already know how to do that integral? So now I don't have to worry about dividing by 0. I cut out the 1. I'm going from 2 to infinity, so it's the infinity symbol on top that makes it improper. Once we do this little change here, then we can continue. We can actually make the jump all the way to this step where we had the value of the integral, since we've done those steps already. So we've got the limit as n goes to infinity of -1/2 natural log of 1 minus x squared in absolute value bars from 2 to big N. So this number back here is finite. 1/2 times the natural log of 3. We're all good there. Now we got to look at that other part. N is going to infinity, so n squared gets even bigger. So 1 minus that becomes minus infinity, right? Well, in absolute value bars, this becomes positive infinity. The logarithm's a growing function. So as x goes to infinity, so does the logarithm. So this part here gets infinitely large, and that's enough to say that the integral diverges. Got to get you pretty handy at doing this, because in chapter 8, we've got a section where this is the middle part of doing the problem. This is what you have to do to get from the beginning to the end. We're going to do something called the integral test when you investigate behavior of series. Okay, now one more, just to bring you back to what we did beginning of the course. Right here, are you still writing? What does the graph of y is equal to 1 over x look like? It's a hyperbola, right? In the first quadrant, I'm just worried about 1 over x. Take the graph of y is equal to 1 over x, revolve it about the x-axis, and I just am interested in the area under that curve from x is 1 to infinity. Revolve that part of it around the x-axis, and you construct something called Gabriel's horn. What I want to know is, what's the volume of that thing? So here's the problem I'm talking about. The region under the graph of f of x is equal to 1 over x. For x bigger than or equal to 1, so here's x is equal to 1. Here's that graph. This region here is revolved about the x-axis, and it creates a solid. It kind of looks like a horn. And I want to know what the volume of that solid is. So we're going back to our volumes of solids of revolution. We can figure out how we're going to do this. You can tell me, and we'll see if this is a finite number. All right, this is your turn. You tell me the plan. What method do I want to use to find the volume of the solid of revolution? Disks. We're going about the x-axis, and it's bounded by the x-axis. So we're going to take this little rectangular region here, rotate it, and we'll get a disk. The volume of the solid is the integral of the volume of one of the disks. That would be a pi r squared, and in this case, dx is the thickness of that rectangle. So that volume is equal to pi times the integral of r squared dx, where r is going to be the height, r1 over x. So we've got pi integral 1 over x squared dx, but we're integrating from 1 to infinity. So that's our improper integral that would possibly give us this volume. 1 over x all squared is the same thing as 1 over the x squared. So we're integrating 1 over x squared from 1 to n as n goes to infinity. I guess I left room for the limit here. So we're integrating x to the negative 2 from 1 to n. That gives me x to the negative 1 over negative 1, which is just a negative 1 over x. From 1 to n. That's pi times the limit as n goes to infinity, negative 1 over n, minus a minus gives me plus 1. As n goes to infinity, negative 1 over n, my gosh, goes to 0 pretty quick. 1 over infinity becomes 0. So this first term is going to be 0. My limit then is just 1. This thing has a volume of pi cubic units. And here's where I wish we had gone over the surface area formula. I skipped it because I said you'll do that in Calculus 3. It turns out that this has a finite volume, but it can hold inside, but an infinite surface area. The surface area integral for this thing would diverge. Finite volume, but infinite surface area. Just one of those things for you to ponder when you're sitting around pondering stuff. You have any questions? Okay, I always skip the section on hyperbolic and inverse hyperbolic functions, but I do want to say something about these functions. Section 7a we're going to skip, and I'll tell you why we're going to skip it. I've spent most of my entire adult life not worried about them, and I think that can save you any grief. You know when you see wires hung between two poles, like electric wires or something like that, they've got a natural sag in them. called a catenary. The function that describes that involves exponential functions, the sum or the difference of exponential functions. Describes that little sag in between the poles of two wires. That sag is defined by these hyperbolic functions. So if that's a pole, and that's a pole, and then you hang some sort of wire in here, may not sag that much, but there is a little droop to it. This curve is called a catenary. I can't spell it, let me read it. D-N-A-R-Y. And can be described by a function of the form y is equal to some version of, maybe some multiple of 1/2 e to the x plus an e to the negative x. You could have some scaling factor here, some scaling factor up in the exponents, but some version of that. That particular expression, 1/2 of e to the x plus e to the negative x, that linear combination of exponential functions is called a hyperbolic cosine, right? That's kind of like a hyperbola. This expression is the definition of the hyperbolic cosine function. We write the hyperbolic cosine as COSH of the independent variable x. You either read that as hyperbolic cosine or you just read it as cosh. The cosh of x is that linear combination of 1/2 e to the x plus e to the negative x. If you take the derivative of the hyperbolic cosine, you just take the derivative of this thing here. And you essentially get this back, except for when you take the derivative of the second term, you're going to get a minus sign right here. That's why y prime is equal to 1/2 e to the x minus e to the negative x. That function is called the hyperbolic sine. And you write it as SINH of x. And you read that as cinch of x, even though there's not a C. Cosh and cinch. One function is the derivative of the other without the minus sign. Guess how we define a hyperbolic tangent? Yeah, cinch over cosh. Now, since we already know how to differentiate and integrate e's to a power, then we certainly know how to differentiate and integrate cinch, cosh, and hyperbolic tangent. So in that case, I'm not going to spend any time going over these. If you ever encounter them in your physics classes or in your engineering classes, just remember that they come from sums of exponential functions, and you don't really have to memorize anything new. Okay? But there are derivative formulas, integral formulas for them, which just follow the derivatives and integrals of exponential functions. So we skip this section, even though I'm going to mention that there is a hyperbolic tangent, which is the cinch. Maybe when you study partial differential equations, physics majors or engineering students, you'll see those again. Okay, so let's skip this section. nice to know that these other functions exist. We have hyperbolic trig identities that kind of mirror our Pythagorean identities and things like that. But they're fun to show algebraically when you start squaring Cinch and Cosh and adding them together. You're really squaring these guys and adding them together. You can almost see why that's going to give us one. Almost. Right? Because what do you get when you multiply an e to the x with an e to the negative x? Yeah, you're going to get a 1. So if just for funsies, you might want to show hyperbolic Cinch squared. Cinch squared plus Cosh squared is 1 kind of thing. Okay, that's the end of chapter 7. That's kind of the end of the like calculus that you know and love. Calculus you know and love involve limits, derivatives, and integrals. Now we're going to cover something brand spanking new for you. We're going to talk about sequences. A sequence is just a list of numbers. If I just called out some numbers here, 1, 2, 3, 4, I'm developing a sequence. It's a sequence of counting numbers. 1, 4, 9, 16, 25. How am I developing the numbers in this list that I'm making? Squaring the integers, right? So the next one will be 36, 49. A list of numbers that follow some sort of pattern is a sequence. Sequence is a list of numbers. To give it a more mathematical definition, we call a sequence a function that maps the counting numbers to a point by doing something to the counting number. You told me in that last example, I'm squaring my counting numbers. 1 squared, 2 squared, 3 squared, 4 squared. So it's a rule that maps the counting numbers to a value. But it's a list of numbers. So let me find my papers. Take that away. I need to keep these in order somehow. It's too late for that. So in section 8.1, how about sequences? Sequence is a list of numbers. So here's some examples. What did I do? 1, 4, 9, 16, 25, 36, blah, blah, blah. That's an example of a sequence. Here's another one. 1, 4, 7, 10. Have I given you enough numbers in that list so that you can predict the next 2 or 3 terms? 13, 16, 19. I'm just adding 3 to the previous term. If you just add a fixed number, here I'm adding 3 to the previous term, you get the current term or the next term. That's an example of something called an arithmetic sequence. what I've just written there in words, where I add a 3 to the previous term, I'm saying that, I'll come back to that. I'll go back. I won't do that now. Here's another example of a sequence. 1, 1/2, 1/4, 1/8, 1/16. What's the next term? And then the next one? So I'm just taking a half of the previous term. When you generate the next term by multiplying by a fixed number all the way through, that's something called a geometric sequence. Seen this sequence before? 1, 1, 2, 3, 5, 8, 13. That's a Fibonacci. That's an example of a Fibonacci sequence. I'm getting, say for instance, I got this term here by adding the previous 2 together. I get the 13 by adding the previous 2 together. Fibonacci sequence. That's something to do with how many rabbits you have if you start with 2 rabbits and they mate. And at the end of each month, another rabbit is produced. And then you've got 3 rabbits and they mate. And it's kind of kinky after a while. So we can develop any kind of list of numbers. I started all of these with 1. I don't have to start them with 1. I could start them with something else, depending on what the rule is. Our notation that when I talk about sequences in general, I'll use subscripted lowercase letters. We'll put our sequence in these cute brackets. And then we'll have some sort of counter down here, a K or an I or an N, whatever you want to use as your counter. And so this develops things, that's going to be some sort of rule, the AN. And so it generates things like A1, A2, A3, and so on. We go out here to a certain part, I can say that I'm at the kth term here. The one right after it is the K plus first term. The one before it is the K minus 1 term. But it's an infinite list of numbers. So our more formal definition is that a sequence is a function whose domain is the set of counting numbers that's the 1, 2, 3, and so on. That's the subscript. And whose, sometimes we use 0 as the first one. So maybe I shouldn't say the counting numbers. I should say the non-negative integers. So sometimes we use the non-negative integers. But anyway, we take either the counting numbers or the non-negative integers and we pair them up with a value, some real number. Usually positive, doesn't have to be. So here's an example of what a graph of a sequence looks like. We've got the counting numbers n, and then we've got some sort of height given by an. So if I start with 1, maybe there's a value here, might go up, might do some more stuff, might go up, and so on. It's a scatter plot of dots. So I'm going to give you some examples where I use more of the function notation and ask you to write out the sequence for me. Let's write out the first 5 terms of the given sequence. Q, give me a Q here. So I'm going to say n is greater than or equal to 1. We'll start our counter at 1. Okay, so I put it in brackets. And then I want you to generate terms by taking the counter, multiplying it by 2, and then subtracting 5. So when you see the expression in brackets, that's how you know you got a sequence. Then you generate the list of numbers just by substituting 1 in for n, then 2 in for n, then 3 in for n. We're going to do the first 5. So what's the first term described by 2n minus 5? Negative 3. Now n is 2. 2 times 2 is 4, minus 5 gives me a negative 1. Now n is 3. 2 times 3 minus 5 is 6 minus 5 is 1. Now n is 4. I have 8 minus 5 is 3. But it looks like I'm just adding 2 to each term, doesn't it? The difference between negative 3 and negative 1 is a positive 2. Negative 1 add 2, you get to 1. 1 add 2, you get to 3. So 3 add 2 is going to give you 5. So that's an example of an arithmetic sequence. The next example, let's go with n divided by n plus 1. Give me the first 5 terms of that. Who wants to call them out to me? What would the 100th term look like? What about the 1000th term? What do you see as we get further and further out? You're going to get pretty darn close to 1. That would be described as the limit of this sequence. After a while, we're just putting a bunch of 1s in this list. After a long while, we're putting things that are essentially 1, right? The long-term behavior will be called the limit of the sequence. So we'll come back and revisit that one. How about the terms here? Take -1 and raise it to the nth power, and we can generate a sequence of numbers. Not an exciting sequence. When the power is an odd counting number, we get -1. When the power is an even counting number, we get +1. So it's a sequence that oscillates back and forth between 1 and -1. So if I were to look at the long-term behavior of this, you'd have to know whether I'm talking about an even power or an odd power. If I want the 100th term, I'm going to get a totally different number than the 101st term. My sequence of numbers bops back and forth between 1 and -1. That's an example of a sequence that does not have a limit. There is no long-term behavior that I can predict. So let me write that down. We say a sequence converges to, say, the number L if it has a limit as n goes to infinity, like in our sequence 2. If we take the limit as n goes to infinity of n over n plus 1, get up here, paper. You remember doing those limits in calculus? Calculus 1? All right, as n goes to infinity, the numerator goes to infinity, the denominator goes to infinity. That was our L'Hopital's rule. So we take the derivative of the top divided by the derivative of the bottom. The derivative of the top and the derivative of the bottom are both 1. So this just gives us 1. So this sequence here, we could write it like this. We could say that that converges to 1. After a while, my dots are all going to be right around there. We also evaluated those kind of limits by looking at the ratio of the powers, right? If the degree on top was the same as the degree on the bottom, then that limit to infinity, after however many applications of L'Hopital's rule, always ended up giving you the ratio of the coefficients of the highest power on n. How many of you remember that? The sequence in the second example, or in the third example, the limit as n goes to infinity of -1 to the n does not exist because these values oscillate. Uh-oh, how do you spell oscillate? O-S-C? About like that. Oscillate between -1 and 1. So that's not a sequence that converges. That would be a sequence that diverges. So in order to have a convergent sequence to a limit L, let's say here's L, it could do whatever it wants at the beginning. It could just start bouncing around, but after a while, they've all got to kind of hover around L. Once you pass some large number n, all of these have to kind of hover around that value of L. You do some wiggling at the beginning, but once you pass that large number, they're all acting the same. So we would have that the difference between the nth term and that limit L can be made as small as possible whenever n is bigger than big N. The limit is L means the difference between the nth term and that limit, no matter which one's bigger, is smaller than the smallest number you can think of, epsilon, whenever n is chosen out in this region here. So I'm going to see if you can remember how to take limits. I'm going to write down a few sequences here and see if you can find the limits of the following sequences. Everybody's doing, did I put anybody to sleep at home? You both said yes, I put them both to sleep. Okay. Next, we're going to compute the limits of the following sequences. Let's go the first one. On top, I'm going to have an n to the fourth plus 3n cubed minus 1 divided by 2n to the fourth plus 4n plus 5. So here's what you're doing. Limits you can do fairly quickly. You do it a lot quicker than I can write it, based on what I said a few minutes ago. What will this limit be as n goes to infinity? 1/2. The degree on top is equal to the degree on the bottom. So even though this has the form of infinity over infinity, if we did L'Hopital's rule several times, we should get 1/2. I'm going to do L'Hopital's rule several times. So here's what it would get. We have infinity over infinity. So I'm doing L'Hopital's rule here. And I get the limit as n goes to infinity of 4n cubed plus 9n squared. The derivative of 1 is 0. Down here I get 8n cubed plus 4. So it still has the form of infinity over infinity when n gets large. So I do L'Hopital's rule again. That's 12n squared plus 18n. Downstairs I have 24n squared. Again, it's infinity over infinity, so I do L'Hopital's rule again. And I get 24n over 48n. Actually, I got an 18 up here. 24n plus 18 over 48n. But I think one more time gives me the limit as n goes to infinity of 24 over 48. And there's the 1/2. You don't have to do all those steps. You can remember that if the degree on top is equal to the degree on the bottom, your limit will be the ratio of the coefficients. What was the pattern if the degree on the bottom was bigger than the degree on the top, and n goes to infinity. It goes to 0 if it's got a bigger power on the bottom. If the bigger power is on the top will always grow faster than the bottom. So it's going to go to infinity. So if you have polynomial type things, and if you have the degree on top equal to the degree on the bottom, say of f of x over g of x, then the limit is just the ratio of the coefficients of the highest power of x. If the degree on top is strictly smaller than the degree on the bottom, then I say that that's a bottom-heavy fraction, which means the bottom grows faster than the top. And if you divide by something that's getting big on the bottom, then that's going to go to 0. If the degree on top is bigger than the degree on the bottom, so that's when it's top-heavy. The top grows without bound as the bottom eventually will disappear, then the limit will be infinite. Either plus infinity or minus infinity, depending on the sign of the terms. If you have something that you're not sure of, maybe it doesn't have degree, maybe it has trig stuff in it or exponential stuff in it, then you can use L'Hopital's rule. So we can always use L'Hopital's rule for 0 over 0 or infinity over infinity. But the more we practice with L'Hopital's rule, the more observations we can find. Like, for instance, here's example 2, find the limit of the sequence. Suppose I have an n to the 100 power, and I divide it by e to the n. And I want to know if that sequence has a limit. I want to know this. Well, I have an n in the numerator, an n in the denominator. I can't really tell about degree because e to the n is not a polynomial. N's going to infinity, so both the numerator and denominator is going to infinity. But is this fraction top-heavy, bottom-heavy? Are they growing at the same rate? Well, I know if I did about 100 applications of L'Hopital's rule, eventually my numerator is going to be a constant. But the denominator is not. No matter how many applications of L'Hopital's rule I do, my denominator has as its derivative e to the n. So eventually I would have a constant divided by e to the n. What does that tell you that this limit is going to be? It's going to be 0. E to the n grows faster than n to the 100. E to the n grows faster than n to the 10 million. So I'll always have an e to the n in the denominator, where eventually my L'Hopital's rule will give me a constant in the numerator. So I can see that this is bottom heavy. That means this limit is going to be 0. What about this one? Suppose I took derivatives here. You guys forgot how to take the derivative of 3 to the n. The derivatives behave much like the derivative of e to a power, except for you get a natural log term next to it. The derivative of 3 to the n is 3 to the n times the natural log of 3. The derivative of e to the n is e to the n times the natural log of e, where the natural log of e is just 1. So all of these L'Hopital rules are still going to give me the same numerator and denominator, but I'm always going to have another natural log of 3 tacked on in the numerator. So can you tell what this limit's going to be? Is it bottom heavy, top heavy, or about the same? It's top heavy, because how big is E? 2.7-ish. Slightly smaller than 3, but 3 to the n is going to grow faster than 2.7-ish to the n. So the 3 to the n grows faster. That means in the long run, this thing's going to become infinite. Right? I'm going to have a lot more in my L'Hopital's rule, natural log of 3's, an infinite number of those multiplied together. So this is going to go to infinity because it's top heavy. So instead of always using L'Hopital's rule, let's get some idea of how fast things grow. I'm going to write down our tower of power. And this will help you remember how fast things grow. Our logarithm is a pretty slow growing thing. The natural log of a number grows slower than that number to any power. The natural log of x is smaller than x. It's smaller than the square root of x. It's smaller than the cube root of x. The natural log of x is smaller than any root of x. So it's at the bottom of our tower of power, the natural log of n. So for instance, I can say that that's smaller than the 4th root of n. How does the 4th root of n compare to the square root of n? The 4th root of n is smaller when I'm talking about counting numbers. So the square root of n would be a bigger number than the 4th root of n, where n to the first will be a bigger number than the square root of n. And then as I increase the powers here, it gets larger. So as I go to n squared, n cubed, n to the 4th, n to the whatever, even if I went, say, all the way up to n to the, I don't know, 100th, we said, then we'd have an e to the n is bigger than n to a power, but 3 to the n is bigger than e to the n. 4 to the n, 5 to the n, 6 to the n, those would be bigger than 3 to the n. So 10 to the n, for instance, is bigger than 3 to the n. Do you know what this number means? N factorial. What does that mean? What does 5 factorial mean? Times what? Right? 5 factorial, 5 times 4 times 3 times 2 times 1. So n factorial means n times n minus 1 times n minus 2 until all the way down to 1. So it's bigger than 10 to the n. But it's smaller than n to the n because I've got a lot of minus 1s here. So n to the n is pretty dang big. So if I have a ratio of terms that behave like that, I can quickly tell whether I've got a bottom-heavy fraction or a top-heavy fraction, and whether or not my limit is going to go to a constant or to 0 or to 1. So for instance, if I wanted to take the limit as n goes to infinity of 6 times 5 to the n minus 2 times 3 to the n divided by 4 times 4 to the n, which would be 4 to the n plus 1, plus 20 times 5 to the n. You certainly don't want to do L'Hopital's rule on something like this. You just want to kind of get a feeling for which term drives the numerator and which term drives the denominator faster than the others. So the one that's acting as the highest power in both the numerator and the denominator is the 5 to the n. After a while, the 3 to the n and the 4 to the n aren't going to matter. It's the 5 to the n that's going to take over. And they both have a 5 to the n in it. So I think it's safe to say that this limit follows these two. The other ones are lower power. So using that same idea of looking at the ratio of the coefficients, this limit should give us 6 over 20, or 3/10. You agree? That'll save you a lot of time trying to do L'Hopital's rule with something like this. All right, so let's think about other asymptotic behaviors. Let's do some more limits. I don't have any more white paper. Ta-da, more white paper. Let's look at the sequence. Continue to find the limits. Find the limit of the sequence. So I'll start renumbering again since I lost track of the numbers. When I just say find the limit again, that's as n goes to infinity. We did one like that earlier. Do you remember what that limit was? Zero, right? Because it behaves as what over e to the n? So the one's a constant, that doesn't grow, the e to the n does grow. So that limit is going to be 0. All right. Let's take 1/2 to the n and add to it, say, arctangent of n. And look at the limit of that. And I'm going to do them separately, because limits are that kind of creatures. We can do them term by term, through a product, through a sum, through a quotient. So when I look at 1/2 to the n, think about what happens as you take higher and higher powers of half. Half squared, half cubed, half to the 10th, half to the 100th. What's happening to the number as you raise it higher and higher powers? It goes to 0, right? A half to the 100th power is pretty dang small. So this term's going to go to 0. What about the arctangent? Do we remember what the graph of that looked like? But like that. You're right, it's like that. When we put an arctangent in here, it looks kind of like this. It has asymptotes. That one here, one here. Left end goes to that negative asymptote. The right end goes to the positive asymptote. Where was that asymptote? That's right. This one's at y is equal to pi over 2, and this is at y is equal to negative pi over 2. So we say that the arctangent of n goes to pi over 2 as n goes to infinity, and the arctangent of n goes to negative pi over 2 as n goes to negative infinity. So back in our example, that second term is going to pi over 2. So my overall limit is 0 plus pi over 2. All right. Let's take the sequence that looks like 1 plus negative 1 to the n. And look at the limit as n goes to infinity. We'll see about this one. Doesn't have a limit, right? Sometimes you have 1 plus negative 1. Sometimes you have 1 plus 1. Those are the only two things that show up as n increases. A 1 plus negative 1 or 1 plus negative 1 or 1 plus 1. So it's either 0 or 2. This expression here looks like when n is odd, right? So this has no limit. So we say that this sequence diverges. If it has a limit, it converges to whatever that limit is. If it doesn't have a limit, here it doesn't have a limit by oscillation between 2 and negative 2, so we say it diverges. Okay, how about n to the negative 1 over n? Is that hard? Easy? Can you get it before you write it down? You need to do some steps. You can do it where the n is. Go up there where the n is. Replace n by a very large number. Negative 1 over a large number. What's 1 over infinity? 0. Negative 1 over infinity is still 0. So this behaves like 10 to the 0. So this has a limit of 1. The sequence converges to 1. n divided by the square root of 4n squared plus 1. So I would say the degree on top is 1. What would you say the degree on the bottom is? It's also 1, right? This little 1 out here doesn't matter. When n is large, you barely even notice that. So this behaves like the square root of 4n squared. The square root of n squared is going to behave like n when n's a positive number. So this should have the same power on top as on bottom rule. What should the limit be then? Should be 1/2. Take the 1 from in front of the n, take the square root of 4. Same power on top as on the bottom. L'Hopital's rule is not helpful here, because if you start taking the derivatives of things with square root sign, you get square root signs back and forth in the numerator. You got to kind of know the tower of power stuff. All right, how about if our term looks like this? N times the sine of 1 over n. So let's do this piece by piece. This first n goes to infinity. And here, as n goes to infinity, 1 over n goes to 0. Sine of 0 is 0, right? So this behaves like infinity times 0. What infinity times 0 is, I don't know. That's one of those indeterminate forms. It can be 0. It can be infinity. It can be 1. It could be 17. Infinity times 0 is indeterminate. So I don't get any information from that. I've got to rewrite this so that it allows me to do L'Hopital's rule. I want to either write this as 0 over 0 or infinity over infinity. So what we did before is we took one of the terms and put its reciprocal in the denominator. The easy one to move is the n. Multiplying by n is the same as dividing by 1 over n. When I move it now, the 1 over n in the denominator behaves like 0, 1 over infinity, and then I have the sine of 0. So I have it in the form of 0 divided by 0. So I can do L'Hopital's rule. That's the derivative of the top divided by the derivative of the bottom. To take the derivative of the top, we take first the derivative of the sine, and we get a cosine of the 1 over n. Then by the chain rule, we go inside and take the derivative of that 1 over n. In simplified form, what's the derivative of 1 over n? No, that's the integral. Negative 1 over n squared. Then down on the bottom, the derivative of that 1 over n is another negative 1 over n squared. So those guys are going to cancel. And all we have to do now is take the limit as n goes to infinity of the cosine of 1 over n. What's that going to be? Well, 1 over n goes to 0, right? What's the cosine of 0? Cosine of 0 is 1. So that sequence converges to 1. It's your lucky day. I have a 7th example. You're ready to scream, huh? Man, this 2 hours calculus. You can scream. That's a whimper. Let's see if you remember this one. So this is generating terms that look like 1 plus 1 to the 1, 1 plus a half, all squared, 1 plus a third, all cubed, 1 plus a fourth, all to the fourth. It is the definition of E. E to what power? E to 0 is just 1. This is the definition of E to the first power, but I'm going to show you why. We're going to go through all the formal steps. Right? This has, as n goes to infinity, 1 over n goes to 0. So the stuff in the parentheses behaves like 1. The exponent behaves like infinity. This is an indeterminate form of exponential type. There were several exponential types of indeterminate forms that you encountered back in chapter 4 when you were in calculus 1, believe it or not. 1 to the infinity, 0 to the 0, infinity to the infinity are indeterminate forms of the exponential type, and you'll approach the limits the way we do this one. A couple of other indeterminate forms are infinity minus infinity. And then the one we've seen before, 0 times infinity. These forms all say do more, do some algebra. And your job is to try to do enough to get it in the 0 over 0 form or the infinity over infinity form. When you have one of the first 3 types, these exponential forms, the technique involves using a logarithm. So we start like this. We suppose that this thing has some sort of limit, and let's just call it L. Then I'm going to take the natural log of both sides. I can move the limit in and out of the function rule, so I'm going to go ahead and move it out and put the logarithm here. And the reason I took a natural log is it's the exponent that's giving me trouble. And I have a log property that tells me that the log of anything to a power is that power times the log of the base. The log property that allows me to bring powers down and write them as coefficients. So you're vaguely remembering this from Calculus 1? Brush up, it's in section 4.5 of this calculus book. When the n comes down and I try to take the limit, then this n is going to infinity. This n is on the bottom, so 1 over n goes to 0, and this behaves like the natural log of 1. Natural log of 1 is 0. So it puts us in another indeterminate form, but one that we could fix. This is the form where we take one of the terms and put its reciprocal in the denominator. The easy one to move is the n. So leave the natural log of 1 plus 1 over n here. Take the n in front and put its reciprocal down here. But now it's in the right form to do L'Hopital's rule. Both of those 1 over n terms go to 0. The log of 1 is 0. So this has the form of 0 over 0, and we just knock out an application of L'Hopital's rule. Derivative of the top divided by the derivative of the bottom. The derivative log of something is 1 over that stuff. Then we go inside the parentheses and take the derivative of the 1 plus 1 over n. And again, the derivative of the 1 over n is a negative 1 over n squared. Downstairs, we're taking the derivative of 1 over n, so we're getting another negative 1 over n squared. So as before, those will cancel. And I'm left with taking the limit as n goes to infinity of 1 over 1 plus 1 over n. So as n goes to infinity, this term here is the only one that's got an n on it. The n's in the bottom, so that term's going to go to 0. And I have 1 over 1 plus 0. So I get 1. But remember, that's the natural log of my limit. I'm interested in the limit, so I take the exponential of both sides to get me back the L. So this limit is e to the first power. Now if I put another number up here, I'll get e to a different power. If I put another thing up here, I'll get yet a different power. Put something down here. So I can change it, but it's all some version of e to a power. But I do want you to know how to do those steps instead of just guessing them. So when we deal with sequences, the main question is, does the sequence converge? If it converges, to what? In the rest of chapter 8, though, we're not going to mess with sequences. We're going to take the terms in a sequence and we're going to start adding them to each other and generate something called a series. And we want to know if the series converges. And if so, to what? So an example of a series would be, I've got a savings plan. Every day I'm going to throw another $1 into a coffee can. Every day I do that. There's $1, next day throw another one in, next day another one, next day another one. I do this for all of infinity because I'm a witch. I live for infinity. At the end of infinity, how many dollars do I have? An infinite number of them. Okay, so there's an example of a sum that is infinite. 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1 is infinite. But if I, for instance, have a pile of, oh, I don't want to do that. The typical one would be, I'm going to walk toward the wall, and my first step is going to have a length of 1. My next step is half that length. Then my next step is a half of that length. So 1 plus a half, plus a fourth, plus an eighth, plus 1/16. Am I ever going to hit the wall? Depends on how far away the wall is, but that sum, 1 plus a half, plus a fourth, plus an eighth, plus a 16th, is a finite sum. So we're going to look at how to discover what that sum will be. So what I want you to practice now are taking these limits, learn your tower of power, and definitely spend the weekend making sure you know how to integrate everything under the sun or moon. You guys are moon people. I can tell by looking at you. When the sun comes out, you guys all kind of fall asleep. Okay, so I'll put up a review sheet and let me know what you need to know on Monday. Kind of go through all the materials so that Monday we can kind of review. 1 week from today is our second test. Get it home? All right, I'm gonna stop this recording here. Maybe. Any questions from anybody at home before I end this meeting? All right, I'm shutting off the meeting. See you guys on Monday.